Hello everyone. Last time we discussed the Newton's law of inertia, where particularly we discussed the concepts behind this law of inertia. Today we're going to solve some mathematical equations or mathematical problems regarding the Newton's law of inertia. So this is the part 2 of this discussion series about the Newton's laws of motion, particularly the applications of the law of inertia. Mathematically, we can describe the Newton's law of inertia as the sum of all forces is equal to 0. This means that the net force acting on the object is equal to 0. We have Fi this is the net force that is acting on the object. Now there are many forces that acts on a particular object. Say for example, if we have here the box that lies at the surface, as we know, the box has a mass, or the particle has a mass. And if we're going to calculate the particle's mass or the particle's weight, which basically is just the force due to gravity, that is equal to the mass of the particle or the mass of the box times the gravitational acceleration. Here, the gravitational acceleration is constant, which is equal to 9.8 meters per second squared. According to the Newton's first law of motion, or according to the concept of the law of inertia, an object will remain at rest or in motion unless acted by an external force. The question is, if the box has a weight due to the gravitational acceleration, why is it that the box does not go towards the core of the earth? Why is it that the box still lies at the surface of the table and it doesn't move? Because basically, if the only force acting on the box is the weight, it's like an outbalance of the forces. While basically, there is a force that balances the weight, and that is what we call as the normal force. As we know, the normal force is a perpendicular force with respect to the surface of contact. So if we have here a box that lies at the surface of the floor or of the table, basically we have the normal force that is perpendicular to the surface of contact of the box and the surface of the table. We also have here some examples. We have, suppose we consider a ball that is moving. Initially, for example, we have a ball that is about to move, and you exert a force for this box or for this ball to move. So we exert a force. Before the box gains a speed, which means that the speed is still equal to 0, there is a resistive force that opposes the direction of motion. And that is what we call as the friction force. As we know by definition, a friction force is a force that opposes the motion or the attempted motion. However, since the box is still not moving and it is only about to move, this friction force is what we call as the static friction force. So we have the static friction force. When the box or when the ball finally moves, where it gains a speed that is not equal to 0, basically there is still a friction force, and that is what we call as the kinetic friction force. So this is the kinetic friction force. In general, the friction force is given by F is equal to mu times N, where mu is the coefficient of friction. Okay, so this is the coefficient of friction. And N is, of course, the normal force. So this is the normal force. And the coefficient of friction is a constant, and it depends on the surface. The rougher the surface, the greater the coefficient of friction. In solving some mathematical problems regarding the Newton's laws of motion, we have to consider this free body diagram, which basically is a diagram that is used to show the relative magnitude and direction of all forces acting upon an object. Say, for example, suppose we consider this box. As we can see here, if the box is not moving and it just lies flat on the surface, there are two forces acting on this box. We have the weight and the magnitude, or the normal force. Basically, the weight points downward, and we have the normal force that points upward. So you just have to actually draw these forces in our free body diagram, just like this one. Now, the direction of the normal force is upward, so that is why we have to draw this upward of this free body diagram, where this is our origin, and basically everything that is drawn upward from the origin is taken as positive, and we have here the negative for those that are downward. So let us try to solve this problem. Example number 1. A 60-kilogram man hangs from the lower end of a rope with a negligible mass. The upper end of the rope is attached to the ceiling. Letter A, what is the man's weight? Letter B, what is the tension force exerted by the rope to support him? Now basically, we can just imagine this one. No? We can. It's better to draw the diagram or to draw the situation for us to really be able to solve easily this mathematical problem. Suppose this is the ceiling, okay? And we have here a rope that is attached to the ceiling. And then we have here the man that hangs himself. Just pardon my drawing. Okay. The man is 60 kilograms. So this is 60 kilograms. So basically, we are asked about the weight of the man. And letter B, we are asked about the tension force exerted by the rope to support him. The tension force, as we know, is a force or the forces on the ropes or cables and so on. And basically, the tension force in this particular problem should be enough for the rope not to break, because basically if the rope breaks, the man will fall. So we have to draw a free body diagram for this particular problem. As we know, of course, to support the man, the tension force should be upward, and we have here the weight of the man, which is downward. So the tension force as drawn in this free body diagram should be upward, and the weight of this man should be downward. And as we know, the weight is equal to mass times gravity. So to answer letter A, the weight of the man is actually just given to the mass of this man times the gravity, whereas we know the gravity is equal to 9.8 meters per second squared. Basically, after substituting 60 kilograms, we have the weight of this man is equal to 60 kilograms times 9.8 meters per second squared, which straightforwardly gives us 588 kilograms meters per second squared. Now here, we have to take note that 1 kilogram meter per second squared is equal to 1 Newton, where 1 Newton is basically the unit of force. Thus, the weight of the man is equal to 588 newtons. Let's try to answer letter B. What is the tension force exerted by the rope to support him? So from here, we have to look on the free body diagram. As we know, mathematically, the sum of all forces should be equal to 0. But what are these forces? These forces are the tension force and the weight. So you actually just have to write it down here. We have the tension force is positive because it points upward, and the weight is negative because it points downward, and this should be equal to 0. Now, since we are asked to form or to calculate for the tension, we just have to transpose this one to the other side of the equal, which gives us the tension force is equal to the weight, but we have already calculated the weight, which is 588 newtons. Therefore, the tension force is equal to 588 newtons. Let's consider this next problem. An unknown object with weight W hangs from a chain that is linked at ring O to two other chains, one fastened to the ceiling and the other to the wall. Find expressions for the tension in each of these three chains in terms of W, and the weights of the ring and chains are negligible compared with the weight of the engine or of this object. Okay, so basically, if this is our object that hangs, this is an engine. Okay, so suppose we denote these ropes to be, this is T1, this is T2, where the tension forces in these ropes are T1, T2, and we have here T3. And obviously, we have here the weight of this object, which is an engine. We have the weight is equal to mass times the gravity. Now here, we can have two free body diagrams. We have the free body diagram of the weight. Okay, so this is the free body diagram of the weight or of the engine. And we also have here the free body diagram of the nut. And we see nut, okay, this one. Now in the engine, we can see only two forces. We have the weight, which is downward, and as we know, this is equal to mass times gravity. And we have the tension force, which is upward. This is T3, which basically is pointing towards the nut. We also have here the free body diagram of the nut, which is this one. And as we can see, T3, with respect to this nut, is pointing downward. We have T2 is pointing towards the left, and we have T1 is pointing towards the ceiling at a certain angle, which is 45 degrees. And we actually just have to solve this following equations. We actually have two equations for this because we have two free body diagrams. Okay. Now for the engine, we have for the engine, okay, we have the sum of all forces is equal to 0, which implies that we have the forces that is T3 minus W is equal to 0. And this implies that T3 is equal to W. For the nut, we have, okay, we have sum of all forces should also be equal to 0. However, if we check this free body diagram, we can see that T1 has actually components with respect to the x-axis and components to the y-axis. So we have here T1, x, and we also have here T1, y. The reason for these components is because T1 doesn't lie on the x-axis and it doesn't lie on the y-axis, which means that it's lying between the x and the y-axis, which leads us to expect that there are components or there are influences with respect to the x-axis and the y-axis. As we can see here, T1x is the adjacent side of this triangle because we can actually draw a triangle here. So this gives us T1 cosine of 45 degrees. And T1y is actually, this is the opposite side, which gives us T1 sine of 45 degrees. Okay. This means that for the nut, we actually have two equations. We have the equation with respect to the x-axis, and we have the equation with respect to the y-axis. So for the x-axis, we get the sum of all forces with respect to the x-axis. And as we can see here, T1x is pointing towards the right, which means that it's positive, and we have T2 points towards the left, which means that it's negative. So we have T1x minus T2 is equal to 0. This means that T1 cosine of 45 degrees is equal to T2 after transposing this one towards or to the right hand side of the equal. As we know, cosine of 45 degrees is square root of 2 over 2. But anyway, we can just write cosine of 45 degrees. So this means that T1 is equal to T2 over cosine of 45 degrees. So this is the x equation, or the equation with respect to the x-axis for the knot. How about for the y-axis? So we have the sum of all forces with respect to the y-axis is equal to 0, which implies that we have here, as we can see, there are only two forces in the y-axis. We have T1y points upward, which means that this is positive, and we have T3 points downward, which means that this is negative. So we have T1y minus T3 is equal to 0, which directly gives, we have T1 sine of 45 degrees is equal to T3 after transposing this one to the other side. And as we know, T3 is equal to W. So we have T1 sine of 45 degrees is equal to W, which gives us T1 is equal to W over sine of 45 degrees. Now the problem asked us to express these tension forces in terms of W. We already are done with T3, which is equal to W. We have T1 is equal to W over sine of 45 degrees. And how about T2? So we have to come back here. Straightforwardly, we have T2 is equal to T1 cosine of 45 degrees, which means that T2 is equal to T1. Okay, we have T1 cosine of 45 degrees. But T1 is W of sine over sine of 45, and we have cosine over sine. It's actually cotangent. So this is T1 cotangent of 45 degrees. Or just 1 over tangent. So I guess that's all. If you have some questions or clarifications regarding these problems, you may just type your comments in the chat box or in the comment section of our video. Thank you so much.